Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's derive the rule on differentiating a sum or difference of functions. For this video, we are going to prove the rule on differentiating a sum or difference. Don't worry about combining them because basically they have the same application, because if we are talking about difference, let's say x minus y, we can just simply rewrite that as x plus negative y. So basically, it combines here. Both of the situations are combined for this given rule on differentiating here. It tells us that if f and g are functions, and let's say h is defined as the sum or difference of f of x and g of x, then if derivative of f of x and g of x exist, then the derivative of h of x, which is first and the foremost the combination of f of x and g of x, is equal to the sum, okay? The sum of their individual differentiation or derivative. So we're going to show that here. So let's say for this form here, we have h of x is equal to f of x plus minus g of x in that case, okay? So if we have something like that, now we are going to show that its first derivative or its derivative is just the sum of the individual derivatives, just like this one here, okay? We are not going to show any example, but we are going to prove this. Take note, I introduced here subtraction, but what happened here is just plus. It's because some of the theorems will not include here difference. But basically, as mentioned earlier, even if we include here difference, this is still addition, because we can rewrite difference as the sum of a positive or a sum of two different expressions, with one of which is a negative term. So let us try to use this theorem here. We have f, this is the not theorem, this is the definition for the derivative. We have here the limit of f x plus delta x minus f of x over delta x as delta x approaches to 0. This is by definition. Now again, other references would like to use h instead of delta x or increment of x for easier manipulation. So x plus h minus f of x. So all the delta x is changed to h rather. So they are just the same, okay? Nevertheless, we're going to use this definition because this is more formal in terms of the discussions based on what I have read, and just to also consider even small changes in the value of x. So this is our goal, okay? We're going to look into that. So here is the proof. So we're going to show this h prime of x. So by definition, okay, we're going to change this to h, okay, per definition. So we have here the limit of h of x plus delta x plus h, sorry, minus, my bad, minus per definition, minus h of x over delta x as delta x approaches to 0. So we're going to show that from here we'll be reaching this portion, okay? So again, let me just, even if this has minus, let me use sum plus, okay? Plus only for our proof. But again, it's also true for subtraction, as we can introduce this as plus negative of g of x, okay? So let us have other portion here or part of our screen as we try for any scratch, okay? The scratch paper here. So h of x is f of x plus g of x. Let's use plus again, plus g of x. So what is h of x plus delta x? Exchanging that here, so this would be equal to f of x plus delta x, as we change this as well, plus g of x plus delta x, as we change that here, okay? Why are we doing this? Because instead of this function and that, which we cannot operate here and say we can minus, no, we cannot do that. We are going to use the representations here on our scratch paper. So let me move further here. The limit of this, instead of that, we'll be using this sum. So we have f of x plus delta x plus g of x plus delta x, okay, minus our h of x, which is actually the sum of the two, okay, f of x plus g of x over delta x as delta x approaches to 0. Okay, hopefully you're following. We are just until substitution. Now I would like us to remove this grouping symbol, considering that this grouping symbol, the two grouping symbols actually, but considering this is subtraction. So what happens here is this will become f of x plus delta x plus g of x plus delta x minus f of x. Now this plus will become minus g of x as well over delta x as delta x approaches to 0. The other purpose of this proof, of course, why do we prove these rules? So that we can of course use them in examples later on. While this may be true for some, even if we don't need the proof, but showing the proof would allow us to really use them freely, at the same time appreciate the shortcuts if there are. So once with this, let me rearrange the terms on our numerator by pairing the f and the g's, okay? Minus g of x. Okay, we're just rearranging the terms. Then I would like us to, of course, look into this. If I'm going to group this and that, and here as well, can we separate them into two different rational expressions? The answer is yes. If we have an example here, let's say 2 plus 5 thirds. This is actually 2 thirds plus 5 thirds. Two fractions of the same denominator. The numerators are these addends here, okay? These addends. So we can separate this. We have the limit, okay? The limit of our f of x plus delta x minus f of x, okay? Okay, I'm doing this, okay? Separate them, delta x plus, you will have here g of x plus delta x minus g of x over delta x. Okay? We separate them just like 2 plus 5 over 3 is 2 thirds plus 5 thirds. Then, of course, as delta x approaches 0. Then, let's distribute the limit. The limit now becomes for f of x plus delta x minus f of x over delta x as delta x approaches 0 plus another limit here as we use one of the limit theorems, distributing that g of x plus delta x minus g of x all over delta x as delta x approaches to 0. So we have separated two limits now. What is this? And what is this? Going back here, this is f of x here, just equal to the representation earlier. So this is just actually equal to f prime of x. And since we are using g here instead of x, this is just g prime of x. So with this now, as our intended goal, we have shown that this h prime of x is equal to that. So finally, we have proven this theorem or rule. Therefore, the derivative of h of h, which is h prime of x, which is a h where h is a combination of f of x and g of x, regardless of sum or difference, is just equal to f prime of x plus g prime of x. So we have proven this identified rule for differentiating sum and difference. So we show this so that in our future computations involving sum and difference, as we look for the derivatives, we can freely use this, because if we cannot prove this, then we are not going to use this. Okay? We will be having examples before proceeding to another rules on differentiation. Thank you very much for watching. So what are you waiting for? Subscribe now.